Hello, and thank you very much for your interest in the research taking place in my group at the University of Cambridge. The topic of this seminar concerns the use of a relatively recent vibrational spectroscopy called Terahertz Spectroscopy. Now, Terahertz Spectroscopy is a method that's been around commercially for about 20 years or so, but it is not as widely used yet as some other spectroscopy methods. As with all methods, it is really important to understand how it works, what limitations it has, and how it complements more commonly used analytical techniques. So in this seminar, I would like to start with an introduction about what we mean by the term terahertz radiation and terahertz spectroscopy, and how this method can be used to learn about organic molecular materials. The term terahertz simply relates to the frequency of the electromagnetic radiation used for this type of spectroscopy. Similar to the word terabyte, the prefix tera simply means 10 to the power of 12. And the terahertz range is sandwiched between the microwave or millimeter wave region at the lower frequency end, and it overlaps with the infrared at the higher frequency end. Now, similar to normal infrared spectroscopy, absorption of terahertz radiation requires a net change in the dipole moment of a molecule as it vibrates. However, terahertz time domain spectroscopy is different, say, from Fourier transform infrared spectroscopy in that we measure both amplitude and phase information of the signal. Now, by combining the amplitude and the phase information, we can then extract the complex refractive index of the sample. As a result, we obtain the absorption as well as the refractive index spectrum, and we can thus think of the method either as a high-frequency extension of dielectric spectroscopy or as a low-frequency extension of infrared spectroscopy. Now, compared to Raman or infrared spectroscopy, where we almost exclusively measure the vibration of individual atoms or small groups of atoms relative to one another, at the lower frequencies in the terahertz range, the radiation excites motions of entire molecules, or at least large parts of them, which are governed by much weaker forces compared to the covalent forces at infrared frequencies. Using terahertz spectroscopy, we're sampling much weaker forces such as hydrogen bond interactions as well as van der Waals dispersion forces. As a result, this method opens a unique perspective to study the interaction of organic molecules. Any subtle differences in how molecules move relative to one another and how flexible they are can be picked up with this method very easily. However, the interpretation of terahertz spectra is much more difficult compared to the mid-infrared. Rather than, say, measuring vibrational modes that are characteristic to specific functional groups, and hence the chemistry of the molecule, these large amplitude vibrational motions are complex in nature, and they're typically strongly coupled between the different molecules. Now, in ordered crystalline solids, there are well-defined vibrational motions that result in clear peaks at specific frequencies. And so here we can see an example of the experimental terahertz spectra of two polymorphs of L-glutamic acid in the blue line on the left. These coherent vibrations are a mix of the so-called phonon modes, as well as the large-scale intramolecular bending and flexing motions. And together they are characteristic for the crystal structure of the system. In effect, the information contained in the spectra in the far infrared is more related to the physical properties of the sample and only indirectly to the chemistry of the compounds involved. In practice, this then means that computational methods are required to interpret terahertz spectra. Starting from the crystal structure, which we can see here on the right-hand side of the slide, it is possible to calculate the vibrational motions at terahertz frequencies using density functional theory, but under periodic boundary conditions. Now, you can see the locations and the intensities of the calculated vibrational modes. They're plotted here as vertical black bars, and together with the resultant spectrum when we apply a constant line width to each of those modes. Now, when we compare the theory and the experiments, it's clear from the plots that there is excellent agreement between the two. And this type of experimental validation of the calculated weak intermolecular forces then provides us with confidence in the fidelity of the calculation. And so in turn, we can then trust the other thermodynamic parameters that are calculated through these DFT calculations and use them to understand the materials. For instance, in this example here, the calculated temperature-dependent Gibbs free energy curve shows that the alpha-glutamic acid is the preferred form at low temperatures, and the beta form is more stable at ambient temperatures. So whilst numerical methods such as computational mode assignments are readily available in a variety of computational codes, there is Crystal, CASTAB, VASP, and many others, this type of calculation cannot be done on individual workstations yet, but it really requires powerful clusters of computers or indeed actual supercomputers. However, by combining this static information from X-ray diffraction with the dynamic picture of terahertz spectroscopy, very interesting insights into the supramolecular chemistry in the solid state, such as solid form identification, phase transitions, some solid state reactions, and other processes can be gained. Now, if we move away from ordered systems to disordered systems, where there's no coherent long-range motion in the molecular matrix, the situation is very different. In the absence of these well-defined structural order, the intensities of the individual vibrations within the condensed phase are no longer localized at these discrete frequencies, highlighted with the arrows here, and hence the spectral intensities of the sharp peaks then collapse into a single broad peak. So instead of several well-defined peaks, there is a single very broad peak which represents the so-called vibrational density of states, or in short VDOS. And this is a universal feature of all disordered materials, no matter the nature of the bonding within or between the individual atoms or molecules. Now, unfortunately, none of the currently available commercial time domain terahertz spectrometers has sufficient spectral bandwidth to measure the entire VDOS peak. Instead, we typically measure only the rising flank of this peak in the range from about 100 gigahertz to 3 terahertz. Now, given the lack of distinct spectral features at terahertz frequencies for all disordered materials, one might really be forgiven to think, well, what's the point of using this technique here? Is it maybe not much better used to study materials that are crystalline and highly ordered, where we have these very nice peaks? And so I would really like to use the following, or the remainder of this seminar to explain to you why I think that despite this apparent lack of specificity, the enormous sensitivity of terahertz spectroscopy to those weak bonds and large molecule amplitude motions does in fact offer a unique opportunity for the analysis of disordered materials in general. And I'll show you later on how it can be applied for pharmaceuticals specifically. So thus far, we've only approached the topic of spectroscopic characterizations from a static point of view, focusing on the chemistry and the physical structure of a material. But to explain the utility of the terahertz method further, I would first like to introduce the role of the vibrational dynamics in organic molecular materials, the link of these dynamics to molecular mobility, and very importantly, its strong temperature dependence. So this is a busy slide here, and we can see an interesting set of spectra really showing the typical behavior in a relatively simple organic molecular material. This is sorbitol here. Sorbitol is an excellent example of a pure compound that can be used as a model glass former, as it doesn't crystallize easily when we supercool the melt. These spectra, in fact, were acquired by Alois Leudel's group in Germany over a very wide range from millihertz frequencies all the way up in frequency to just below the terahertz range by using several different dielectric spectroscopy instruments. When we compare these spectra with the vibrational spectra in the infrared that we've seen before, two characteristics are immediately obvious. Rather than having a large number of sharp and well-defined spectral features, there appear to be only two processes that can be observed over 15 decades of frequencies: the primary and the secondary realization processes. And the other characteristic that is very prominent is that the spectral features shift a tremendous amount in frequency as the temperature of the system is changed. And we transform the sample during cooling, say, from a supercooled liquid at 400 Kelvin into glass and temperatures well below the glass transition, which for this system here is 268 Kelvin. And also highlighted here in red on the slide, we can see the spectral region where the Terahertz spectroscopy method can complement now these dielectric spectroscopy measurements. Now, as we can see here, albeit in slightly different colors on this representation, using Terahertz TDS, we can achieve this flawless, seamless transitions between dielectric spectroscopy data and the terahertz range. In this plot, we can also very nicely see the rising flank and the maximum of the VDOS peak. As mentioned previously, the spectral bandwidth of the typical spectrometers is not sufficient to resolve the full peak, but what is imminently clear from the experimental terahertz spectroscopy data is that the VDOS exhibits quite different temperature dependence compared to the primary and secondary relaxation processes. The peak frequency of the VDOS is only exhibiting a subtle shift here as the temperature is decreased. This is not too surprising, considering the fundamentally different nature of the motions underlying the different spectral features here. The dielectric relaxation processes, of course, are thought to reflect the highly cooperative molecular motions, such as hindered rotations and translational motions in the condensed phase. And their relaxation times are often found to be correlating well with, for instance, viscosity. That's, for example, described by the empirical law of Vogel, Fulcher, and Tammann. In contrast, at terahertz frequencies, we capture vibrational dynamics of these large amplitude motions that are characteristic for weakly bonded molecular materials. And in solids, the timescales of these vibrations at terahertz frequencies are largely independent of whether or not the entire molecules are translating or rotating at the microscopic scale. At a frequency of 10 to the 12 Hertz, the relaxation time of the process corresponds to 10 to the minus 12 seconds, so picoseconds. And highly cooperative rotations and translations do not take place on these picosecond timescales. They take much longer, of course. So in summary, this schematic here provides a very useful representation to put terahertz spectroscopy of disordered organic materials into context. At low frequencies, we can observe the dielectric relaxation processes, which originate from highly cooperative molecular motions and show strong temperature dependence. In contrast, at the high frequency in the infrared, we measure vibrations of atoms and small groups of atoms that are characteristic of the chemical structure and are not strongly affected by the molecular interactions. In between, at terahertz frequencies, well, we have a photon energy of a few millielectron volts, or around about 1 kilojoule per mole or so. The radiation is sensitive to subtle changes in hydrogen bonding, as well as weak dispersive forces. So we observe complex vibrations of entire molecules or large parts of them. And by exciting organic molecular materials at these energies over a wide range of temperatures, we can study the presence and nature of interactions between molecules in a unique way. So put together, the characteristics discussed thus far mean that terahertz spectroscopy is a very sensitive technique to probe mobility of molecules in liquids and disordered solids. Now, we first explored the utility of the method at the example of a set of 4 polyalcohols, 2 of which, sorbitol and glycerol, are widely used as a set of model glass formers with characteristically fragile and strong liquid behavior, respectively. What we can see here are the loss spectra of all 4 materials as they were heated from liquid nitrogen temperatures all the way to room temperature. Now, in all cases, the spectral shape is characteristic of a disordered material, and in this log-log plot, the shape of the VDOS is clearly visible. Here we can, what we did is we chose to plot the spectra in terms of the imaginary part of the dielectric losses, so epsilon double prime, to make it easier to compare the spectra with dielectric spectroscopy data. It's useful to note that the shape of the spectra would be the same no matter if we plotted them in terms of absorption coefficient alpha, as alpha and epsilon double prime are directly proportional to one another. Now, even though there is no significant shift in the peak position, the absorption, or in this representation, the loss of the imaginary dielectric they change considerably, in particular as the temperature exceeds the glass transition temperature, Tg, which is here highlighted in red. Now, upon cooling, a molecular liquid at Tg undergoes the transition into the glassy state. The time required for relaxing the structure of the system begins to exceed 100 seconds. That's an entirely kinetic process, which is universal to any disordered material, and can of course be studied by a wide range of experimental techniques. And so to investigate this process in a bit more detail, it's helpful to extract some key information from all the spectral data. Given the lack of multiple distinct spectral features in the VDOS, we can now just choose a single frequency and compare the change in absorption or the losses between the different materials. And so here we can see a plot of the changes in dielectric losses at a frequency of 1 terahertz for all those 4 materials. The data are offset vertically for clarity. And as all 4 materials have a different glass transition temperature, the x-axis is scaled relative to the calorimetric glass transition, which corresponds to the primary relaxation process and hence is referred to either the T alpha or the Tg alpha. Now, what is immediately apparent is that with increasing temperature, the absorption or dielectric losses increase quite considerably in general. That is not too surprising, as the intensity of the dipole moments in the sample is expected to increase as increasing amounts of thermal energy are supplied and the molecular mobility in the system increases. Furthermore, we can observe a strong change in absorption at the glass transition temperature. At temperatures above Tg and below the Tg, the change in absorption with temperature appears linear in both cases, and there is a clear difference in the gradient at Tg. This behavior is also intuitive if we consider that the glass transition process is associated with a significant change in molecular mobility as the cooperative motions, such as hindered rotations and translational motions, are commencing at experimentally observable timescales. Now, at terahertz frequencies, we do not measure these motions directly. These motions are what's captured by dielectric spectroscopy, and they result in the spectral feature referred to as the primary or alpha relaxation process. But instead, at terahertz frequencies, we do measure the mobility associated with the microscopic motions of the bending and flexing of molecules, as well as their relative displacements towards one another. Besides, the plot of the change in absorption losses at terahertz frequencies for the 4 polyalcohols here also reveals that there is a second transition point at lower temperatures, where there's a change in gradient of the terahertz absorption. This is a more subtle process, and the temperature of this point marks the glass transition of the so-called Johari-Goldstein secondary or beta relaxation. Now, to better understand this observation, it is useful to start by putting the terahertz spectroscopy data into the context of results from other experimental techniques. And so on this slide, we can see the terahertz data grouped together with the relative shift that we can measure in the OA stretch vibration frequency using infrared spectroscopy. We've got light scattering data here, mechanical properties such as the loss factor we can measure by dynamic mechanical analysis. We've got here the mean square displacement of molecules measured by neutron scattering, and we've got NMR data here grouped together. And in all those cases, with all these different techniques, we can see the change in gradient associated with the glass transition, so the primary relaxation. Upon closer inspection, we can also see in all datasets there is actually a change in gradient associated with the secondary glass transition, the Tg beta. So both glass transition processes clearly can be observed over a huge range of frequencies. However, the phenomenon of the secondary transition has thus far previously largely escaped the attention in the community. Most likely because of it's a relatively weak effect, and it almost falls within the experimental noise. A lot of experimental work, of course, has focused on processes at higher temperatures, and hence this low temperature effect has somewhat got unnoticed. However, the terahertz spectroscopy method is really fast experimentally, and it can be carried out within a laboratory very easily. And so given the high sensitivity of the method, there is far less noise in these measurements compared to many other techniques. So the effect is maybe more obvious, and that's why we got interested in it. Of course, this observation is not unique to sorbitol, but it can be observed in all organic molecular materials. Here are some further examples from the literature for a non-hydrogen bonding rigid molecule such as ortho-terphenyl, for instance, as well as a linear polymer such as polymethyl methacrylate here. And in all those cases, the TG beta can be observed. So what physical processes are associated with this secondary glass transition? Given that we can observe the processes with such a multitude of experimental techniques, it is clear that the observation of TG beta must originate from a shared fundamental origin. And this seminar paper here by Marty Goldstein holds the key to understanding the data, I believe. In this paper, Goldstein outlines how the underlying shape and structure of the potential energy landscape determines the dynamics in disordered molecular materials, which explains the frequency independence of the observations. He argues that the molecular motions at low temperature are dominated by the existence of potential energy barriers that are large compared to the available thermal energy, and hence molecular conformations are locked into their glassy state. When sufficient thermal energy is available to overcome those energetic barriers, localized motion is possible, which become then a precursor to the primary glass transition at high temperatures. At the time Goldstein submitted this paper in 1968, it was not possible to perform suitably accurate molecular calculations to describe this phenomenon more quantitatively. However, with the availability of modern supercomputers and suitable ab initio molecular dynamics methods, it is now possible to calculate the molecular motions with sufficient accuracy and to account for anemonic effects, as well as to calculate sufficiently long trajectories in these dynamics calculations to capture the molecular dynamics of the process adequately. What's very interesting is that we can use the variable temperature terahertz data to validate the molecular dynamics calculations. Given their unique sensitivity to the weak intermolecular forces, and given the fact that the terahertz excitation sample large amplitude vibrational motions, an agreement between the theoretical spectra at terahertz frequencies and the experimental measurements provides a lot of confidence that we need to then trust the subsequent interpretation of the data that we get out of the MD simulations. So here we can see the experimental terahertz spectra for sorbitol on the left and the MD simulation on the right, and there's excellent agreement between the two sets of data. Now, using this MD method, we can explicitly calculate the volume occupied, in this case by 10 molecules of sorbitol in the disordered condensed phase, as a function of temperature. And the results here, these green-filled pentagons in this plot, are in excellent agreement with the experimental data from all these different methods that we showed before. Now, to further explore the temperature-induced changes in the dynamics of the system, we can carry out an analysis of the O-CEO dihedral angles in sorbitol in the glassy state. And we can do this as a function of temperature. There's a busy slide here, but you see that in the top left, there are three distinct structural features corresponding to dihedral angles of approximately 60, 180, and 300 degrees, with a submaxima within the regions emerging as the temperature is decreased. Now, significantly, the onset of the localized subregions occurs near 260 Kelvin, which is the corresponding TG alpha of sorbitol, while significant localization occurs near 180 Kelvin here, corresponding to the TG beta of sorbitol. An analysis of the time evolution of dihedral angles in glassy sorbitol helps to uncover the changes in atomic dynamics that occur as a function of temperature in such disordered molecular solids. For instance, at temperatures below TG beta, only small magnitude oscillations of each dihedral angle about its respective average value, with little to no structural rearrangements, are occurring, implying that the molecules are confined to the subminima in the potential energy surface. However, as the temperature is increased above TG beta and through TG alpha, the magnitude of the oscillations increases and fluctuations in the subminima become increasingly prevalent. Now, we can understand the results in terms of that below TG alpha, structural changes are localized, while temperatures above TG alpha lead to large-scale conformational rearrangements of the molecules. While this phenomenon is associated with overcoming potential energy barriers, the origins are slightly more complex. As the barrier heights, and indeed the entire potential energy surface itself, are equally dynamic as the processes themselves. Now, this arises because the potential energy surface, which dictates the atomic dynamics and the structure, evolves in time as the interactions themselves change, with various factors influencing sort of the structure at any given time. For example, intermolecular anharmonicity, which is responsible for thermal expansion, can lead to a larger accessible free volume of the particles with increasing temperature, or the molecules with increasing temperature, which in turn can weaken the intermolecular interaction strength and thereby lower potential energy barriers for conformational rearrangements. In summary, Terahertz spectroscopy is an interesting method to investigate the change in vibrational dynamics with temperature in disordered molecular materials. So in particular, at temperatures below the calorimetric glass transition, the TG that's normally referred to, the method, or the Terahertz method, can resolve the mobility of localized motions, which play a significant role in the physical stability of glasses. Terahertz spectroscopy is a very sensitive method, and given that high-quality spectra can be acquired in less than a minute, it's possible to perform measurement over a wide range of temperature in a day and carry out repeat measurements using relatively simple laboratory equipment. So you can really go through a lot of samples and build up confidence in the measurement results. As with all techniques, though, it's not a silver bullet that can give the answer to everything, but instead it must be used within the context of its strength and, of course, by augmenting complementary techniques. So I hope that this general introduction has provided you with a bit of a flavor for what the technique can do, what it can't do, what its relative strengths and weaknesses are. And I'd like to go on in a subsequent video explaining you the applications of this technique for different research areas. Thank you very much.